modalities. But given the time and that people are tired, let's make more than a journal club, a conversation, okay? So interrupt me with questions. If we get there, we get. If we don't, we don't, okay? So let me use this one. And so let me tell you what would be the goal. So what I'll try to explain is the context, first the context on which the papers I wrote in the last year are, okay? So what am I trying to do first, okay? So consider a field theory that at very high energies is a conformal theory, right? Consider something in 4 dimensions, but at very high energies is a conformal theory. And this theory, at some scale, at some energy, is deformed either by a relevant operator or by a BEV to a relevant operator, right? So this conformal theory in principle had different symmetries. Characteristically, this will break part of those symmetries, right? And there will be some RG flow, right? And let's consider a situation in which this infrared theory presents phenomena like confinement, symmetry, some symmetry breaking, etc. Right? So it's a strongly coupled quantum field theory, see, not conformal anymore, with certain interesting features. Okay, so that's the picture in which I would like to be working. Because this is strongly coupled, when I tried, and by the way, all this is in the context of holography. Okay, so in the context of holography, one will be working with a solution in string theory, a classical solution in string theory, where for large values of a certain radial coordinate goes to some ADS5, okay? Depending on the global symmetries of this field theory, there will be some internal manifold, okay? And so this also, say, plus some 5-form gauge field. Let's, if you wish, we can explicitly say this in the case of n equals 4 super Young Mills. So this M5 is going to be the phi sphere, and there is that field only. And what will happen, or the equivalent to this thing and this flow, is that in a subleading way, subleading at infinity, I mean, in some radial, in this radial coordinate, these other fields, in this case in type 2b, will be switched on, okay? Then deforming the original metric and producing some flow, right? That in principle will be associated with that RG flow. And what one would like is to have here smooth smooth background. By smooth, I mean something without any singularity, right? If this were possible, then what one would have is a way of calculating phenomena like this in a consistent way, right? By consistent, I mean here that the corrections to what we calculate are always smaller than what we have already calculated. Is this more or less clear? Yeah. Questions, interrupt me at any point. Don't hesitate. Particularly the young people, don't hesitate. Okay, very good. So this is what one would like. Okay, and this idea, as I'm proposing here, was proposed by Girardello, Petrini, Porratti, and Zaffaroni by first time in this year, and then by Polchinski and Strassler. in the next year. And the main problem that happens with this approach is that here you can obtain a solution, but it's not smooth. Okay? So it's a solution where Ricci scalar or other contractions diverge, right? Or other fields diverge. So the problem you encounter is that while maybe in these regions are capturing in a faithful way this part of the dynamics, as the moment you try to learn about this phenomena, you are calculating in a non-consistent way. Namely, the things that you don't calculate, they are bigger than what you have calculated. This is okay, yeah? So the problem that motivates part of the things I was doing is how can one do this in a correct way, okay? In a good way. Okay, so let me tell you things that people tried since 2000. Okay? So of course, people try to improve on this, but always they find that they find solutions where the smoothness is lost. Okay? Tell me, Nathan. Well, so this is quantum mechanical and very quantum mechanical. That's why in the duality you want to be classical all the way. You can, so in this particular case, this is a supersymmetric situation. These solutions break some of the supersymmetry, and certainly global symmetries, the moment you switch these zones, these isometries will be broken, right? Supersymmetry will be broken. All these solutions have this feature. Yeah. The solutions are stable, are supersymmetric. You solve first-order equations, but they're singular. Okay, so that's the Pedro. You had one? No, okay. Very good. So let me mention something. This is a conceptual bit. The reason one would like to have a UV, having an ADS, or in other words, having a CFT in the far UV, is to be as Wilsonian as possible in the sense of being able, on this side of the duality, to use what's called holographic normalization. So this is what motivates this being an ADS5, okay? The possibility of using that very solid technology to calculate correlation functions of operators in this field theory by doing semi-classical calculations here. Okay? So that's a very well-defined system. So people try different things since the 2000s. Let me very schematically tell you what are the things, and again, please stop me, particularly the young people. Many things here are old, so people need not know them. So Klebanov plus a long list of very good co-authors, among which you count Witten, Nekrasov, Gapser, Zeitlin, Herzog, and of course, many others, but these are the main papers where what I'm going to tell you now is set. They propose the following. Okay, let's start not with that field theory, but with a very not so complicated quantum field theory where there are two SUN gauge groups and some bifundamental matter joining them. Those are bifundamental fields, sorry. Okay? And when to this field theory you add this superpotential, this is in the context of n=1 theories. When to this field theory you add a superpotential like this, well, let me write it. this particular field theory happens to be a conformal theory, and strongly coupled conformal theory. By which I mean that these fields acquire anomalous dimensions that are large, in this particular case, given by this. Okay? So one is starting, unlike in this case, where this field theory you can make weakly coupled or strongly coupled, and you can move the coupling as you wish. In this case, the field theory is strongly coupled. Okay? So you don't know very well how to write the kinetic terms, but thanks to supersymmetry, there are many things you can learn about this field theory. So the proposal of Klebanov, this is the theory proposed first by Klebanov and Witten, the proposal that Klebanov, starting with Nekrasov and Gapser, and then completed with Zeitlin and Strassler, sorry, and then Herzog, is the following. Okay, let's deform this theory, the equivalent to this deformation there, in this way. This is another number, M, right? Right, so instead of having two SUN gauge groups and by fundamental matter and a superpotential, what you have is one SUN and one SUN plus M gauge group, same by fundamental matter, same superpotential. Okay? Thanks to the magic of supersymmetry, you can learn a lot about this RG flow towards the IR. Okay, so this is a very exact results. So you can learn that this will undergo a succession, a cascade of what are called SAIFR dualities. We can go over the details if you wish. But the end of that cascade, if it happens that N is a multiple of M, so if these two numbers are commensurable, then it happens that the end of that cascade is some SUM field theory, some Goldstone, and that's the far infrared, right? So it's a field theory that one expects it confines, breaks some symmetries. I can give details on that, but it's a very well-controlled system, okay? So Klebanov proposed that theory because he knew what to do, or this is what he achieves in all these papers, how to write here a supergravity background that captures all these dynamics. Okay, so that's the reason why he went over this. The supergravity background, let me tell you briefly how it looks. Let me write it, and by this I will mean Minkowski in 4 dimensions. And some internal phi manifold. It's a well understood phi manifold, and just let me tell you at this colloquial level, this manifold has all the global symmetries of this field theory. Okay? We can go in details if you wish. There is also in these backgrounds some phi form that lives in there, some 3 form, and in some cases a dilaton, that they take values in here, basically, in here and in there, okay? The main characteristic I want to emphasize about this is that this function, the function can be written exactly analytically in terms of an integral, but let me tell you how it looks in terms of this radial coordinate. At very low values of the radial coordinate, which is equivalent as very low energies, or at very high values, which is equivalent at high energies. So the way this function works is such that here goes to a constant, plus some correction, R squared. When you calculate the Ricci scalar, Ricci tensor, etc., this function is perfectly smooth in here. Yeah? This means that phenomena like the confinement and the symmetry breaking that gave place to this Goldstone can be very precisely understood with this system. Yeah? But when you look at it in the UV, it goes like this. Some number. Log of R. Okay? So if you remember how the work factors go in an ADS solution, typically they go like this. So what one would like is this function for very large values of R to be that in order for the solution to be asymptotically ADS and being able to apply this holographic normalization. But it doesn't go exactly like that. Picks up this logarithmic correction. Okay? So the presence of this logarithmic correction makes very hard to implement holographic normalization. Okay? So this is a very nice system, but it has the problem that calculating correlation functions is very hard, next to impossible. Okay? One needs to solve lots of equations, and this log actually makes it very hard. I'm not saying impossible, but it's very laborious, for sure. Okay? This is what not having an asymptotic ADS brings into the problem. So you see here a situation where if the IR, or small values of radius, is not smooth, the UV is well defined, and conversely in this kind of systems, is smooth in the IR, but is not asymptotically ADS. Okay? Okay, very good. So what happens is that you don't, the question by, the question that you're asking is, what's the UV of this system? Okay? You would like to be exactly this, right? This is what one would like. What happens is that the moment you introduce this deformation, you miss this UV, okay? And what happens if you continue the thing, you continue somewhat this cascade of cyber dualities towards the UV, okay? What you will encounter is something where this is what happens in the first cyber duality. You increase by that, then you go one more, n plus 3m, n plus 2m, etc. So you grow the number of degrees of freedom without bound. Okay? So you might say, and I think this is a correct thing to say, that the UV of this situation is not field theoretical. Okay? Put it differently. You could calculate something like the central charge here, and you will find that grows with that logarithm. So grows with the energy. Okay, so it's not a field theoretical behavior of this R, so of this energy. Okay? Any other questions or comments? Please let me stop so people can comment or ask. Okay, Pedro? Right. So the connection comes in the following way. If you consider first that this n is much bigger than this m, this small deformation you are making here, right? This can be understood as what you are deforming, similar to QCD, is with a quasi-marginal coupling, right? What you can find in this theory, from this viewpoint, is that the beta functions are logarithmic with the energy. And that logarithm is this logarithm when you calculate it in the UV. So, in other words, you never undo this deformation, right? This deformation keeps on propagating when going to the UV, missing the fixed point. Okay? And what you can find in this theory, from this viewpoint, is that the beta functions are logarithmic with the energy. And that logarithm is this logarithm when you calculate it in the UV. So, in other words, you never undo this deformation, right? This deformation keeps on propagating when going to the UV, missing the fixed point. Okay? Yeah. So you would like to start here and go down, but if you were to continue what the supergravity gives you towards the UV, at some point you will overcome this situation and you will be counting more and more and more degrees of freedom. Right? It's like the system is asking for you for a UV completion, right? To not stop being field theoretical. Yep. Okay. Good. Let me tell you. Yeah. Yeah. So, or it's not what one would like, right? I mean, it's a correct metric in the sense that solves the Einstein's equations, solves supersymmetry equations. It's not the dual of this thing I wrote here, right? Because this deformation is not undone like there. Yep. Okay. So that's the way you could think it, right? So put it in this way: the supergravity is giving you a solution that is what it is and not what one would like it to be. Okay? It's not a precisely, like in this case, a relevant deformation. Right? It's not a relevant operator. This operator keeps on influencing the UV. Whatever deformation it is keeps on influencing the UV. Let me tell you a third one because it will come handy from what I'm going to discuss. Any question or comment? Yeah. Yeah. To this never-ending cascade up. Okay. Yeah. It's always the thing is that you will never undo this number. This number is encoded in the integral of this F3 on some 3 cycle inside this manifold. Okay. So what one would have liked is this integral to depend on the radial direction such that it becomes 0. But it's not the case. This is an integer number all along the solution. Okay? So there might be some other solution, maybe. Nobody was able to find it. Okay? Let me tell you a third approach that people have done. The approach is conceptually very dirty, for reasons I'm going to explain, but it's very easy to work with it. So people have done lots of things, and it gave a lot of inspirations and field theory results. So the approach is the following. And let me take as a representative a paper by the master in 1999. Very nice, very, very to the point paper. There he proposes to take a stack of D4 branes. So where a 4+1 quantum field theory with 16 supersymmetries lives. Right? Field theory not phenomenologically very appealing, and do the following. Put these 4 branes on a circle in such a way that you will give periodic conditions to all bosons in that theory and antiperiodic conditions to the fermions in that theory. The thing will break SUSY completely. Okay? And it will be such that if you calculate the perturbative spectrum, it will look like this. And I want to emphasize on the word perturbative spectrum. At 0 energy, there will be a gauge field. At some gap, there will be a fermion and a boson. And these Kaluza-Klein modes will keep on appearing. Okay? And the Kaluza-Klein can be understood basically on the fact that you are reducing on a circle with certain boundary conditions. okay? So again, this is the perturbative spectrum of the theory, but you may think that if you find a metric representing this situation, at very low energies, the field theory will be basically Young-Mills. Okay? And then, after some scale, it will be corrected by these other fields. Okay? So such metric is found. It looks very nice and very simple. So it's in type 2A. It looks like this. R is going to be the radial direction. These are the 4 Minkowski directions that you have here. There is a function of R that appears in this direction that is going to parameterize that circle. And then basically there is a radial direction. And then there is a sphere. Okay? There is also a dilaton here that is proportional to this. And there is also a 4 form that basically lives on the 4 sphere that I'm putting there. Okay? So when one looks at this function f, let me write it for you, is something like this. Yep. So what's happening, or the way this could be read, is the following. Notice that as this coordinate r goes to infinity, as r goes to infinity, this function f goes to 1. Yep. And basically that's a 1, that's a 1. And this metric is the metric of 4 branes. Okay? So you encounter there 4 branes, you encounter there a 4 plus 1 dimensional quantum field theory. Yep. So a field theory that needs some UV completion. Instead, as r goes small, in particular when r goes to q, yep, this function will vanish, but this part of the space will vanish if one chooses appropriately the periodicity for phi in a smooth fashion. So the space is smooth. Okay? So there is no singularity at all in here. You have to be careful when R goes very large, the dilaton goes large, and you have to UV complete the system in some way. In this case, going to M theory. Okay? So the reason why I'm mentioning this type of system is because it's a bit of what happens there, in the sense that you have smooth IR, but the UV is very much not ADS. Okay? Needs of some UV completion. Okay? So even more, one could say it's not field theoretical, the UV. Okay? So needs of someone to do something with the UV. In this case, that something is going to M theory and finding the theory in terms of M5 branes. Okay? So why I'm mentioning this? Because here you have another situation where, with this background, you can calculate very trustably things about the infrared of this field theory. But as you go to the UV, you have to change. This is not anymore a nice system to calculate with. Okay? So the reason why I told you all of this is because what I want to tell you is how to make something that takes the best of these systems. Okay? Yeah. There is another thing that one would like, and let me write it here, and then I'll erase over there. Can this be seen from there? Yeah. There is another thing that I would like to add here, that is, notice that in all these systems have fields that transform in the adjoint representation. Say, for example, all these fields on the D4 brane, they transform all in the adjoint. All these fields, if we start from n equals 4, they transform all in the adjoint. Here, you have at least a bifundamental field in the fundamental here and in the antifundamental there, and vice versa. But it would be, so you have these bifundamentals. But one is missing basically what are fundamental fields. Fields transforming in the fundamental. What you may call quarks. Okay? And in supersymmetric situations, as quarks and etc. Okay? So these setups are missing the point, if you wish, are lacking in the following things. Either they are infrared singular, or they are ultraviolet not ADS, and they all miss the presence of fundamental fields. They all miss the presence of quarks. Okay? So what I would like to tell you is how to improve on these things, having a situation where, so this is the improve I wanted to tell you. We will have fields in the adjoint, fields in the fundamental, fields in the bifundamental. We will have smoothness of the background, and we will have asymptotically ADS. ADS5 in the particular case I'm going to tell you now. Is this okay? So what I'm going to tell you now is how one can do this thing, make it work, okay? And you will see that conceptually the thing is not very far from this type of brain wrapping a system, but with a twist to the story that will bring this into the game. Okay? Any questions or comments before I continue? Let me make time to erase a bit there. I promise, Nathan, that I keep it to 1 hour. So at 5, we leave, no matter how, okay? Raining or not. Well, you see, I prepare lots of details about those field theories, but there is no point. Let me go to the point. Okay, let me erase here. Tell me. Agree. But actually, let me elaborate on this because it's a nice question. So Pedro is asking the following: is there any need for a background to exist? And let me, because you are asking a pure question, let me answer with a pure theory, right? Let's take Young-Mills. Just Young-Mills. So, okay. So this is the perfect theory, right? We know this is the energy, and this is the Toft coupling, SUN Young-Mills. Okay, so we do know that the Toft coupling goes very small at large values of the energy, and we believe, lattice and etc., that at certain scale will start to go large and will present a mass gap. Right? So the spectrum will be global 1, global 2, etc., etc. Right? So this is a perfect theory. Now, your point, is there any background dual to this? Well, as you are pointing, this coupling goes to 0, right? So this points to the fact that whatever is the holographic dual, whatever is the holographic dual will have to be strongly curved. Strongly coupled, strongly curved. Namely, only string theory could do it. Okay? So there needs to be a background, certainly not with the present technology, right? What one is doing actually here, in all these things, what one is doing is actually this, or what one would like to do. Where the one is here. Okay? So a theory that asymptotically goes to a conformal point, but strongly coupled. Yeah? Yep. This is what can be done with present technology. This is what I mean. Asymptotically goes conformal and strongly coupled, and then goes strongly coupled. Yeah? Truly strongly coupled. This implies that, and this is something that can be touched from there, that this theory typically has different scales. And what one would like is a situation like this. This is what you would like, and that's the confinement scale, and these are other scales, and they are very separated. So the thing goes always strongly coupled, so the one is there, but there is a good separation between these scales, okay? What one obtains in this supergravity approximation is a situation where, okay, asymptotically you go strongly coupled, but these scales are almost degenerate. This UV completion is almost degenerate with the interesting scale, okay? Put it in this system here. This is, as I said, is the perturbative spectrum, but when you look at the non-perturbative spectrum, what you find is that you find, okay, it's gapped. There are some globules belonging to Young Mills, but immediately after them, there are other globules that they are not in Young Mills. They are, for example, charged under this SO5, okay? So you get these extra states, people refer to them as Kaluza-Klein modes, and you get them almost degenerate with the states you're interested in, okay? So if one were able to calculate with the sigma model on this background, the string sigma model on this background, one would be in a situation like this. If one were able to calculate with the full string theory, one would be in a situation like this, where you separate those scales. If you were able to calculate with the full string theory, then one would be in a situation like this. Okay, so we are very far from this kind of things. Is this okay? Yeah, okay, very good. Very good. Let me erase this and tell you what I wanted to tell you. You okay with this, Pedro? You okay with what you say? Tell.
Conceptually, I'm a little bit confused about plotting Toft coupling and not some physical observable. But that is probably the same thing. I could plot some cosine signs.
Yeah. You could plot that and see the influence on it of these Kaluza-Klein modes. Okay? Yeah, plotting a beta function is not physical, indeed. A beta function is not physical, it's scheme dependent. In these cases, say that one thinks about the one loop, and with that one gets an intuition. Very good, very good. So, let me tell you So the idea, 15 minutes more, the idea of how to add this, how to have a situation where you have adjoint fundamentals by fundamentals, asymptotic ideas, and smoothness, okay? So all these things are things that have been worked out in the last 10 years, in particular, two developments by Andrés Anabalón and Horacio Anastase will enter towards the very end of the conversation. So, how to achieve these goals? So the idea will be the following. One will start from a CFT. It's going to be actually a SUSY CFT. The supersymmetry here is playing the role of allowing us to solve the equations of supergravity. Is not so needed, but okay. Start from a SUSY CFT that contains by itself fields in the adjoint, in the fundamental, and in the bifundamental. Then perform a deformation that will be SUSY partially breaking, but partially preserved, and will lead to a smooth background. Okay? And you will see what's the technical price I pay to do this. The technical price will become very clear very soon. Okay? So this can be done in a very controlled setup, but the technical price is very sharp. What I will consider, okay, what I will consider are certain n equals 2. This is not yet the technical price. Superconformal field theories in 4D. Okay? These field theories are going to be very special. They are going to have many gauge groups. Yep. P-1 gauge groups. There's going to be by fundamental matter joining them. Yep. And there's going to be flavor symmetries, quarks, if you wish, for each one of these gauge groups. And this I will denote with this. These are the fundamental fields, okay? So here you have fields in the adjoint, and n equals 2 superconformal, n equals 2 vector multiplet, here, 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 SU1, SU2, etc. By fundamental fields, fields that transform in the fundamental of N1 and in the fundamental of N2, and fields that transform in the fundamental of N1 and under SU F1, okay? So this is what we call quarks. These field theories, they must satisfy, to be conformal, and this is very specific to this n equals 2 in 4 dimensions, they must satisfy a set of equalities that you will see very quickly the deformation law. Here comes. So you see what's happening is that twice this number is equal to the number of flavors, the number of all fields that transform in the fundamental here. So twice N1 is the number of fields F1 plus the number of fields N2. Twice N2 is F2 plus N1 plus N3, etc. So put it differently, this is the statement that the beta function of an n equals 2 theory is 2nc minus nf. And this is a one loop exact result, right? This is the magic of n equals 2. So this continues up to Okay, so I'm going to consider these particular field theories. And I'm going to consider them, and you see how here you start seeing the technical price, in the situation in which the number of nodes is going large. This is what will allow, also all the NIs will have to go large. This is what will allow a trustable supergravity description. Okay, so it's a technical restriction. But you see how, in doing this, one is going a bit away from that initial picture of QCD or Young-Mills, right? One is adding a lot of monsters. Let me tell you very briefly that these field theories have a holographic dual. Okay. In this particular case, there are, by the way, what I'm going to tell you can be done not only in 4, but in 5 and in 6 and in 3 and in 2 and in 1 dimensions. In this particular case, this holographic dual was constructed by Maldacena and Gaiotto. And the holographic dual looks like this. Let me write it and then we stop for any questions you may have. So the background contains an ADS5, a 2-sphere, a circle, and 2 coordinates, yeah, that I'm parameterizing with sigma and eta. The background contains, is in type 2A, contains a Nebel-Schwarz reform, a 1-form gauge field, a dilaton, and a Ramon 3-form. And in order for them to preserve these symmetries, it happens that the B2 lives fully inside the 2-sphere, lives there. The A1 lives in this direction. And the C3 lives in the 2-sphere and that direction. Notice that this background has the following isometries. The isometries of ADS5, say SO24, the bosonic part. The isometries of the 2-sphere, so you have the isometries of the 2-sphere, the isometries of the circle, and these are precisely the global symmetries, the bosonic part of the global symmetries of the 4-dimensional n equals 2 conformal theories. That's the conformal group. That's SU2 times U1. That is called the R symmetry group. Okay, so this type of backgrounds has everything to be related to that. The possibilities you have here is that you can have functions and all these functions, they can only be functions of these 2 coordinates. Otherwise, they will break the isometries. Okay? So the system is quite well defined, and then you say, okay, if you impose SUSY on this system, what you find are 8 BPS equations for these functions F1 up to F8. The BPS equations, they are nonlinear, first order, partial differential equations. In spite of the complexity of the system, the equations can be solved, and I'm going to tell you very briefly something about them, very briefly. the equations can be solved. And the way one solves them is, just let me tell you, it's a technicality, but it's a nice technicality, so I'll be brief. One can write, operating with these BPS equations, one manages to write each one of these f's in terms of a function and it happens that this function, this auxiliary function, v, that you introduce, solves actually a linear partial differential equation that looks like this. And I'll tell you in a second what is this. So the problem of finding a solution dual to that particular type of field theories reduces in the end to solving this linear partial differential equation when you look at the boundary conditions and the initial conditions in order to not generate singularities and etc., one can see that this problem looks a lot, it's not exactly the same, but looks a lot to a Laplace problem, a problem that we solve in electromagnetism, where there are there are two conducting planes with a density of charge say at sigma equals 0. Okay, so basically the way you solve this problem in electro, you solve this one. Basically separation of variables and imposing certain boundary conditions and initial conditions. Okay, I can be more detailed, but let's not do it in the interest of time. So let me tell you here, there is a lot of technology, but let me tell you in detail. This R of eta is a function that basically captures the numbers in the quiver. And also at the same time captures, I can tell you later how you construct this function R, captures these relations, okay? So the numbers can very precisely match. And so the idea is that if you solve by separation of variables, so the solution ends up being a series this is a Bessel. This is a Bessel in sigma. It's a Fourier Bessel series. Fourier in eta, Bessel in sigma. And this coefficient ends up being the Fourier transform of that function R. Okay? All right? So this captures, and one can see this is a very precise thing, how this background with these functions determined in this way knows everything about that field theory. Data, go. No. So it could happen that some f be a constant, right? In some particular situations, that will be a particular of these quivers, right? A very special one. That happens to be integrable. By the way, the string on that background is an integrable system. But in principle, these f's, via this function v, solving this equation, and these f's will know all these numbers, etc. Right? Such that when you calculate the charges, what are called the charges for that field, that curvature, and that one, you will reproduce precisely what would be the Hanani-Witten setup that gives place to that. Okay? Yeah. Any other question? I know this is a lot to swallow, but please ask me and then we can discuss. Very good, very good. Let me go there because it's a good point. The theory that was in the 1990s, the preferred, so what Nathan is pointing is there has to be a case that is the simplest. This is the theory that was the preferred in the 1990s, is in the first paper of Seifert and Witten, right? Notice that in this case, these conditions are not attained, in particular this one, okay? Yeah. So this system is the worst possible, curvatures will be large in this case, okay? Yeah. Then you can start inventing theories that are sort of simple. This is one. Okay. Still is not in the good approximation, piece 2, but okay, there you can start talking, okay? You can think about a theory like this. Sorry. Yep. And this is also simple in the sense. And all of this is captured in this function. Whichever is the theory is captured in this function, okay? All right. So do you allow me 5 more minutes and I'll tell you what we do using Horacio and Andrello. Okay. Okay, let me see where can I do it. Probably here. Let me do it here, and so we keep this. So what we did very recently, among other things, there are solutions by Andrés, here in the audience, Horacio, also in the audience, Simon Ross, and Marcelo Sharso, that are solutions, in principle, that started their life in 5D gauged supergravity. Okay? The moral of these solutions, you may think them in this way, is that you have a stack of D3 branes. This is a type 2 way of thinking them. You have a stack of D3 branes. So you have n equals 4 super Young Mills. And the deformation you produce is very similar to this one that Witten produced. It's very Witten-like, but with a nice twist. Namely, you put the theory in a circle, but unlike Witten, what Andrés and Ross invented was a way of mixing the symmetries of this circle with the R symmetry of the theory. In this particular case, is SO6, is n equals 4 super Young Mills. This mixing of the R symmetry with the symmetries of the circle preserves SUSY. This is very useful to preserve some amount of SUSY, leading to situations that are smooth, like in the case of Witten, but also SUSY preserving. Okay? This is in the first paper of Andrés and Ross. Then with Andrés and Marcelo, they complicated this, adding more degrees of freedom into these dynamics, more freedom, the possibility of adding BEVs, etc. But always the backgrounds are smooth, SUSY preserving, and they indicate, as you can see from here, a transition between a 4D CFT into a 2+1 quantum field theory that one can see confines, and breaks some symmetry. Etc. Okay? So what we did lately was to implement this deformation that they have in this kind of situations, right? To make it work here. It produces backgrounds that I'm not going to write. They are quite complicated, but they all have this form with the following difference. They all have the same ingredients there, but this is the main difference that occurs. Instead of the ADS, you will have these backgrounds of these authors. Okay, these 5-dimensional backgrounds of these authors. So occurs the following, and very similar expressions that I wrote there for the Ramon fields. The following things do change. These functions are not anymore of sigma and eta, but also depend on the radial coordinate, like in the Witten case, or in these cases of Horacio and Andres, etc. So they depend on something else. Still, there is this picture of a potential function, etc., but now the functions are a bit more complicated. And interestingly, as you saw, I made a difference there. There is a vibration between the R symmetry, that is this U1, and that part of the space, and this SU2 and that part of the space. I can give you details of this. It's very simple to give details, but in the interest of time, let me not. What can one do with this? And this is completely simple. And what I'm going to tell you is you ask me if you want details. What can one do with this? So notice that now one has a situation where one has a background that starts from a CFT in 4D, conformal and supersymmetric, and flows in the infrared to a theory in 2+1 dimensions. Far infrared is 2+1 dimensional, and confines, and all the background is everywhere smooth. The things that one can do is one can now say, okay, I will calculate the Wilson loop, say on that or on any of these gauge groups. What one finds is that while in these papers by these authors, because there are no fundamental fields, the Wilson loop confines or gives a confining an area law. In this case, the presence of the fundamental fields deforms the things in such a way that you obtain something like a phenomenon of screening. Okay? But that's one thing that, let me not tell you more, is purely numerical in the end, so it's not nice to tell in a seminar. And there is another thing, and with this I finish. One can find something like a central charge. Yep. And this central charge, when you plot it in terms of the energy, or in terms of the radial direction there, is such that it goes to 0 in the far infrared. That's an end point of the space where the theory becomes 2+1 dimensional. So it goes to 0 and asymptotes in a monotonic way to the value of the CFT4, whichever is the CFT4 you decided to start with. Okay? So it's producing something like one would like, right? A monotonic quantity starting from a conformal point, ending in a gap system. So the system below some energy has no degrees of freedom. Question? No. Okay. So just to finish, let me mention that there is a very interesting universality that appears here. Let me write this thing. One can observe that for some observables, not all of them, right? Not all of them, but some observables will have a shared dynamics between this very complicated n equals 2 theories or these deformations of Andres and Horacio, etc. So there are many things that from field theory would have been very difficult to have an intuition or predict that from geometry is very clean and simple. Okay? So with this, let me stop. It's 10 minutes past the hour. I know you want to leave. Thank you. Well, they're smooth in the sense that they don't preserve curvatures, they don't present curvature singularities, but they are deformations, very non-trivial deformations, in the sense that these functions pick up now a radial dependence, right? Which is very difficult to have an intuition for had you not had these solutions. Okay? So the having of these solutions inspires very simply what will go there and there and there and there and all the others, such that the Einstein's equations, all the equations are solved. It's still very important. It's still very important because part of these functions are still written in terms of this function B. No, the equation is the same that I wrote before. So, yeah, exactly. No, this breaks half of those. So preserve 4 supercharges, okay? Yeah, there are many nice things. There is a lot of structure here, but okay. Just let me leave you with those things there, that there is some phenomenology you learn, how screening will work. And this universality, I think, is a nice thing, okay? Then with these kind of things, one can do many other things and have been done, etc. Right? Thank you for tolerating this at this late time of the day. Right. So this is tell. Well, pi r square, right? The area of the. Yeah. No. Indeed. So in this case, it's simpler to calculate. Not the circular. I mean, it can be calculated. Not the circular Wilson loop, but this one. Separate weighted time t, separate the distance cell, weighted time t, destroy, right? So what you get is L times t, right? Yeah, and that's what you get. So the prescription is the one you know. Basically, you propose that the Wilson loop is proportional to the Nambu-Goto action of a classical string that you use as a prop here, right? So nothing beyond this calculation. The presence of these flavors somewhat breaks that law, giving a perimeter law and showing you screening. Basically, what happens is something like this. Let me just tell you this very briefly. Suppose that you work with a quiver like this. Suppose, just to have an example. No, this is the thing. Screening is a 1/n effect when you have few quarks and many colors. That's what people in lattice call quenching. In here, you have as many colors as flavors because these numbers are commensurate, right? So you don't have the right to claim quenching, okay? So suppose you take this quiver, just to 5n, sorry. Yep, 5 plus 3 is 8. 2 plus 4 is 6, okay? So, okay. So, and you say, okay, I'm going to calculate the Wilson loop on this node, okay? So you put a probe, and the thing is that now this string can explore these internal directions. Okay? Of course, can explore all, but the exploring of this is particularly interesting. So what the string does is, suppose that this is the radial direction, it moves in the radial direction, but also starts to move in the direction of the flavor group. So the string is giving you something like this, and for this one finds a very nice, suppose that L is the separation of the quark anti-quark, and E is the energy of the string. So for very small separations, you find the 1 over L, that's the conformal. As you keep on separating, the thing goes linear for a while, but then at some point, stabilizes, okay? So what's happening when you look at the profiles of these strings, and this is the thing that you have to do numerically, and I would like to have it analytically, but don't, is that the string is exploring the radial direction, but also is deforming in here. At some point, gets here, and the energy ceases to change, right? So this is precisely conformal to confining to screening. We get this numerically, and we got a nice formula that reproduces this phenomenologically, right? Reproduces precisely this type of shape, right? Exactly. The idea is that if P is not large, the background I write will not capture faithfully this thing, will show singularities, right? So the moment you make P large and N large, those singularities are far away, say. If you take this P and you take it larger and larger and larger, what happens is that this goes confining, but at some point will turn, okay? So, okay, yeah, there is a lot of nice phenomenology and yeah, that. Thank you. Very nice. By the way, how antagonistic you are with the speaker before? How antagonistic both of you are with the speakers. No, not me, but these others before. Ooh, I was thinking, ooh. For less than that, in Swansea we go to the parking lot to fight.
Have you done this also with the ABS code?
No, I didn't do it. Maddie's trying with your phone.
Yeah.
It's going to.
And this is then with the ABS code will be like also an equal to.
Is that called n equals 4 or 3?
Yeah.
But there is